In this video, we're going to fly through the answers to this Year 12 electrostatic summary sheet. So let's kick off. Charge is caused by the presence or absence of electrons. How many electrons are contained in this? Well, this is a negative number, so we know that it is an electron. And we know the charge on an electron is 1.602 times 10 to the minus 19. And so we just simply type those numbers into our calculator, and we push execute, and we get 2. So there are 2 electrons in this one. This is a positive number, and so when I divide by minus 1.602 times 10 to the minus 19, I'm going to be getting a negative number, and so it's actually there are an absence of electrons, so there are more protons than electrons. And so I get 3 more protons than electrons and 2 electrons for that one. This milli is a really important idea, and so we're doing the same thing by dividing by negative 1.602 times 10 to the minus 19. And if you go up to options, F6, F6, F1, so F6, F6, F1, you'll get milli, micro, nano, pico, and this is milli, and so I can go minus 3.2 millicoulombs, which is really 3.2 times 10 to the minus 3, but if you don't know that, you can use a calculator, and I'm going to divide it by negative 1.602 times 10 to the minus 19 again, and this time it's going to be a large number of electrons. So we're looking at 2 times 10 to the 16 electrons, and we know that negative and negative, so that must be electrons. So for number 2, we're just going to do the opposite. So if there's 5 electrons, then we're going to multiply by the charge on a single electron, and we'll type that into our calculator, and we get a charge of 8 times 10 to the minus 19 coulombs, capital C. And the same for B and C, we times it by 1,000, a million, and we times, and so that gives us 1.602 times 10 to the minus 13 coulombs, and this is talking about electrons, and so it's going to be a negative charge. This is talking about electrons, so that's going to be a negative charge. This number should give you, should ring bells, 6 million electrons. By definition, that is what 1 coulomb is, and so you're essentially getting 1 coulomb, and again we're talking about electrons, so it's negative. Let's have a look at question 3. Calculate the strength of the electric field. So that is E between 2 plates that are 0.23 meters apart and with a 1.5 volt battery. So we're just going voltage divided by distance, and then we can stick that into the calculator. And we're getting 65.2 volts per meter. Question 4, we're looking for the voltage, so we're going to rearrange this equation so that it's voltage equals ED, and we're going to multiply those two numbers together so that E is the 530, and the volt distance is 1.7, and you notice that it says centimeters, which is times 10 to the minus 2. Say you didn't know what centimeters was, you could go to your calculator and go 530 times 1.7, and then you click this little button here. Oh, actually, it doesn't have centimeters. Sorry, you just have to know that there's 100 cents in a dollar, so it's 100th. And anyway, that gives you 9.01 volts. Question 5, how far apart D are the charged plates? So if we're looking for D, we're going to put the D up and the E down. So D equals voltage divided by electric field strength. We notice a little trick here that they're talking about centimeters, which is a little bit confusing, and so we're really looking at 4.5 divided by 3.2, which would give us 1.4, and because they're talking about centimeters there, the answers here are also going to be in centimeters. Question number 6, a positive charge of 1.602 times 10 to the minus 19 is found in the electric field. Can you determine the size of the electric field? Well, we know electric field is going to be the voltage, which is 200 divided by the distance, and the trick there is that's in millimeters, and so you can use the millimeter function over in your calculator. So I could put 4.0 millimeters, and that give me the same answer. And just to show that that's actually the same as going 4e minus 3 we do get the same answer of 50,000 volts per meter. Heading now to B, calculate the force on acting on that charge. Well, we know that F equals EQ, we know that E is 50,000, and the charge is positive 1.602 times 10 to the minus 19. We put that in our calculator, and we're getting a force of about 8.01 times 10 to the minus 15 newtons. Now, which direction will that force be on that positive charge? Well, we know that opposites attract, and so this is a positive plate and this is a negative plate. This is a positive charge, so it's going to experience a force in the downwards direction. D, if the charge moves from one plate to the other, so that's a distance of D, calculate the work done. So we know that work is force times distance, and we know that force equals EQ, and so that's EQD, which we also know from our formula sheet is equal to EP. And so we know that there is a 50,000 volt per meter electric field. We know the charge is 1.602 times 10 to the minus 19, and the distance from one plate to the other is 4 millimeters. And we know that 4 millimeters is 4 times 10 to the minus 3, and so that'll give us the energy of 3.2 times 10 to the minus 17 joules. Does the magnitude of the force change depending on its position in the electric field? Well, because these are two sets of parallel plates, the electric field is going to be uniform inside of here. What that means is that the field strength stays the same the whole way through. So these are perfectly vertical lines that are perfectly equally spaced, and you can clearly see that I'm not quite doing that right. And so as long as they're inside this part of the field, the force is F equals EQ, and so the E is the same and the Q doesn't change, and so therefore the force doesn't change. However, if we were to take the charge outside of this uniform part, say we were to put the charge over here, then yes, it is possible for that force to be a little bit different because the electric field is different. But we're essentially saying inside this uniform field, no, the force is constant. Question 7, two metal plates separated by a distance of 3 millimeters, so 3 times 10 to the minus 3. On the diagram below, draw some arrows, and so it has positive at the bottom, and we know that electric fields go from positive to negative. So these are nicely equally spaced lines that touch each end, and then we have to have the non-uniform bits on each side. It looks something like that. Show the electric field strength, so we're looking for E equals V over D, and we know the voltage is 20 volts, and we know the distance is 3 times 10 to the minus 3. Chuck that in the calculator, and we get the 6.67 times 10 to the 3 volts per meter answer they're looking for. And so we've got E equals V over D is one way of working electric field strength, so voltage divided by meters. That's just what we've got there. We've got F equals EQ is our other equation. If we rearrange that, we get E equals F over Q, and so the other unit is going to be newtons per coulomb is the other way of working that out. An electron is released with zero velocity from the negative plate, so we can see it up here, a little electron. Describe what happens to the electron once it's released in terms of the energy change. So here it is a negative electron, and so it has electric potential energy, and it wants to move towards the positive plate. The electric potential energy is changed or converted into kinetic energy, therefore gains kinetic energy as it approaches the positive plate, therefore accelerating downwards with an unbalanced force, and that unbalanced force is from F equals EQ. Calculate the velocity which the electron hits it. So it's very similar to previous questions that we've done. So we're going to be using electric potential energy equals EQD, and we know those values. So electric field strength, we've already calculated the charge on an electron, which is negative, and the distance between them. If we chuck that into our calculator, then we'll get an answer of 3.204 times 10 to the minus 18 joules. This is the amount of energy it's got, and so it's going from one plate to the other. Then we're going to be saying, well, that energy is also going to be equal to the kinetic energy. We know that kinetic energy is equal to half mv squared, and so if we're trying to solve for v, and so we're saying that a half mv squared equals that, and so velocity equals 2 times this number, divided by the mass, which is 9.1 times 10 to the minus 31, and then all of that square rooted. So you can just put this into equation solver if you're not very confident, or you can just multiply this by 2 divided by 9.1 e minus 31, which is the mass of an electron. You're going to get a negative answer. You can't get the square root of a negative answer, so I'm just timing it by -1 before going through. And so you get this big answer here. And if I divide it by 1 times 10 to the 6, then I can get that it means 2.6 times 10 to the 6 meters per second. Okay, now looking at question 8. An electron gun, also known as a cathode ray tube, is a device that produces a stream of electrons. It consists of these two plates. The negative plate is heated, causing electrons to, boy, what an interesting idea, be excited so they can be attracted to the side and pulled off the surface. These electrons then accelerate in the electric field between the plates. There's a hole, and so you see the electrons will go flying through this hole. In a particular region, the gun plates are 0.032 meters apart, and there is a supply voltage of that. Calculate the electric field strength. You'll notice that these questions get very repetitive because there's not really much stuff that they can actually ask you, and so they're either going to play with your units or try and add some sort of context, and this is a really common context, the cathode ray tube. Calculate the electric potential energy lost by a single electron when it reaches the positive plate. So again, very similar to the last one, it's going from one plate to the other, and so the distance there is still this distance. They try to mess with you in that case as well, trying to check, do you know which distance to use. It talks about a single electron, and so we know the charge on a single electron is negative 1.602 times 10 to the minus 19, and we've been given the distance already, and we'll chuck that into the calculator, and so we get this answer of 2.56 times 10 to the minus 15 joules, and we can ignore the negative sign because the negative doesn't really have much sense in terms of energy. It does in terms of direction. So it then says calculate the speed, and so now we're saying that EP equals EK all over again, which is a half mass times velocity squared, and so we're timesing by 2, dividing by the mass. So velocity is 2 EP divided by the mass square rooted. If you're not very good at the algebra, that's fine. You just type it into equation solver. So 2.56 times 10 to the minus 15 times 2 divided by the mass of an electron, which is 9.1 times 10 to the minus 31, and that number will be given to you, so don't stress out too much. And so we'll times this by, in this case I'm going to times it by -2 because that answer should have really been positive anyway, and then I divided by the 9.1 times 10 to the minus 31 kgs, which is the mass, and then I square root this answer and divide it by 1 times 10 to the 6. So that is moving very fast with a velocity of 7.5 times 10 to the 7 meters per second. If this number is times 10 to the 8, so 3 times 10 to the 8 or higher, then you know that's impossible because you can't go faster than the speed of light. So for D, explain in terms of work done why electrons lose electric potential energy when they accelerate in the electric field. Explain in terms of work why electrons lose electric potential energy. Well, essentially they're losing electric potential energy because they're over here in the negative, and they're on the negative plate, and opposites attract, and so they don't like each other, or there's a force F equals EQ pulling them to the side, and so that they've got the maximum amount of electric potential energy they can possibly have here, and as they come to the side, that electric potential energy has been converted to kinetic. So if we read this answer, when the electron is at the positive plate, it has the most amount of electric potential energy as possible. Work equals force times distance, so, and force equals F equals EQ, causing the electron to move a distance d from the left-hand plate to the right-hand plate. Because the force is causing the charge to move a distance, work is being done because work is force times distance. This work is changing energy from the potential energy, the maximum potential energy it has on the left, to the maximum kinetic energy it has on the right. Question number 9. Sean is in the physics lab using a mass spectrometer, otherwise known as a Millikan oil drop. An electron is removed from an atom producing a positive ion. the positive ion is accelerated by a constant electric force between the two metal plates. The positive ion is created 1 centimeter, so now we've got two different distances. So this is the D for E equals V over D, and this is a D related to the energy. The positive ion is accelerated towards the top, so that'll be 4 centimeters rather than 1. Draw an arrow to show the direction of the electric fields. So if this is a positive ion and it's attracted to the top, we know the opposites attract, and so it's going, that must mean that this side is positive, and so that must mean the electric field is going from positive to negative, because the top plate has to be negative for that positive charge to be attracted that way. And just says draw an arrow, it doesn't say draw the electric field line, so that's fine. Now the next one, the current between the plates is this, which is symbol I. How many positive ions reach the top plate in 1 minute? And so 1 minute is not an SI unit, so we're looking for 60 seconds. And so we've got I equals Q over T, and so we're really looking for Q. So Q equals I T. The I in this case is 3.5 times 10 to the minus 6 amps, and the time is 60 seconds. And we can simply type that in the calculator, and we're getting 2.1 times 10 to the minus 4 charges or positive ions reaching the top plate in that amount of time. Explain what happens to the size of the electric force as it reaches it. So there is no change as electric field strength E and the charge Q are fixed. So F equals EQ. You always provide an equation, and you could also go E equals V over D and say V is fixed, as is the distance between the plates. When we come down to look at D, explain what happens to the maximum velocity of the positive ion if the power supply voltage is increased. So if V goes up, then electric field strength must also go up, and you always have to relate it back to an equation from E equals V over D, and then you can, so triple dots like that would mean therefore F increases from F equals EQ, therefore acceleration increases from F equals MA, so a faster velocity. You could also argue from a different perspective. You could also argue that EP equals EK, which equals a half mv squared, which equals EQD, and so if E goes up, velocity goes up. So that's another way of arguing for D. You can use these arrows, they're fine. A couple more words is potentially more helpful. The electric force on the ion, so the F is 3.2 times 10 to the minus 15 newtons. Calculate the strength of the electric field between the plates. And so we've got F equals EQ. We're looking for E, which is F divided by Q. We've given the 3.2 times 10 to the minus 15, and we're looking for the charge. And it does say a positive ion, doesn't it? So that's saying that it's just 1.602 times 10 to the minus 19, and positive meaning that that answer there is positive. And so we can type that into our calculator, and we're getting an electric field of around 20,000 volts per meter. I show the maximum velocity of the positive ion if it moves from the position shown to the top plate. Is that the mass of the ion? Is that? And so we're using the same thing all over again. Hopefully this is getting really repetitive. So we're looking at EQD, and so you've got your 20,000, you've got your charge and your distance from the position shown to the top plate. So the position shown to the top plate, that distance there is going to equal 4 centimeters, or 4 times 10 to the minus 2 meters. That's how far it can move. It's attracted upwards, and so that distance there is going to be the 4 times 10 to the minus 2 meters, which will give us our energy. So I can leave that answer stored on my calculator. I can times it by 1.602, and that's a positive number because it's a positive ion, and the distance it can move is 4 centimeters, and so I get an energy of 1.28 times 10 to the minus 16 joules, And like we've done in other examples, velocity is 2 times the energy divided by the mass square rooted. And so we're going to go 2 times that number. The mass is given to us in the question is 5.31 times 10 to the minus 26. And if I square root all of that, so go times 2 in my calculator, divided by the mass, and then square root. And if we've done it right, we should get the same answer, 6.9 times 10 to the 4 meters per second. Boom, done. I hope that was helpful.